All right. Good morning, guys. I hope you are doing well. We want to continue the notes, what we began the last time, I think 2 days ago. And we will start first again with a word of prayer. Father, we thank you. We bless your holy name. We commit this session into your hands. We pray that you lead us, grant us the understanding, and help us remember on the day of the exams. In the name of Jesus. Amen. All right, so let's continue. Yesterday we looked at Bernoulli equation. We looked at mass balance. Today we want to intensify a little on the Bernoulli equation and look at it around pumps. Then we go to how to calculate the friction uh, coefficient or the friction factor, HF. First, when the flow is laminar, and secondly, when it is turbulent, the kind of equations that are involved. So we'll be looking at the Moody diagram. That's the Moody diagram, right? Yeah. So we'll look at the Moody chart and we'll see how to read it and how to go about our calculations. So let's just go straight to today's session. I would like to give a recap, but the time is very short. So I may not go back. Yeah, I may not go back. So I'll just go to today's work. And as we move on, when you find at any point in time, when you have any kind of question, just ask, be free and ask so that I address it before we continue. Okay, you can place it in the comment section or you can speak into the microphone. And please mute your mics. So far as it's not a question, so far as it's not a contribution, please mute your mics. Okay, do that for me. Thank you. And Otieko, please bring to my notice whenever there is a question. All right, thank you very much. All right, so let's continue today's session. Let's continue today's session. My hope is that today we'll solve at least 3 questions after going through the theory we'll be doing. And our next topics that you can just note it down. Our next topics will be momentum balance. Today I may give an introduction if we are able to finish early. Momentum balance and flow meters. And I think that will be the complete thing for the fluid, for both note A and note B. So we'll be done with fluid by then. So if you're able to achieve what we have to achieve today, then these 2 topics will be for the next time we meet. And the other sessions will be solving questions. All right, so the pump work. Today we want to look at pumps. The pump work from the notes. And before I even continue, something unfortunate has happened. Our writing pad is not around. So bear with me if the writing is not looking that good. But I hope you are able to read and, note whatever you have to note. Okay, so pump work. Now, we have to understand the operation of a pump before we can even do a balance around it. We have to understand what a pump is, what the pump is used for, the features of the pump. Okay, so from the notes, that's 6.5 pump work. The definition for a pump is given. The flowing fluid to increase the mechanical energy of a flowing fluid. So this mechanical energy can result in 3 things. Three things. Oh man, I thought this won't come today. All right, so it's fine. I hope. One. That's bad. We can't write. We can't write. Okay, it increases. It
I think we may
can,
just have to continue.
okay. It can increase the velocity. Oh no. To as kinetic energy to a certain extent, in some sense. Or finally, it can increase the pressure. Now, if you know these things, let me see. Can I use? Oh no, I can't write it this. All right, so if we know these things, we will be able to understand the general Bernoulli equation concerning pumps, and we'll know how to go about it. We should also note that whenever a pump is supposed to do its work by pumping a fluid, obviously, there will be a kind of friction that will be caused in the pump. And we will have to always calculate for this friction loss, okay, due to the pump. We have to always calculate it. And because of that, it will be included in our Bernoulli equation. That's for pumps. Now, let's go to the efficiency of a pump. How the pump works, okay, is such that a fluid flows in, then the pump increases its mechanical energy, then it flows out. Now, this is what you have to understand. There is a certain energy supply to the pump. This energy is supposed to cause the pump to increase the mechanical energy of the fluid it is pumping. But because of friction and other parameters which we won't look at, we will look at only friction. Because of friction, the efficiency of the pump won't be 100%. Oh, shit. It won't be 100% as we want it to be because of friction losses. So there is a formula to help you know how much energy you inputted into the pump and how much work the pump was able to do with that energy considering friction. Is that fine? So that formula, let me go to my slide too. That formula is giving us the efficiency of the pump is equal to the useful energy. Now look on the screen. What did I just do? I'm coming. I just did something. Okay. I'm sure you can still view my screen.
Yes, please.
All right. So the efficiency of the pump is given by this. We can see that useful energy, that's the energy given to the fluid, okay? And the total energy, that's the energy supplied to the pump. So it's giving us output on input. So the energy given to the pump and how much work the pump was able to do with that energy. So the useful energy. Now, if you know this, I think you will be good to go when it comes to questions with pump work. Now, I mentioned that the reason why you don't expect 100% efficiency is because there will be friction losses. And this is given us or represented as this is the work of the pump or the total energy supplied to the pump. And it should have been the same for the numerator for we to have, if it was times 100% efficiency. But because of friction, there is minus HF. Remember yesterday I mentioned that this represents friction. So HF of pump, that's the friction of the pump. This is all over. So this is what causes, this is what we call the work done by the fluid and by the pump, or the useful energy, or the energy given to the fluid. Do you get it? And this is the energy supplied to the pump. Okay, so we want to continue. Now there is also a parameter called work of shaft. Work of shaft. Shafts are in pounds. It is minus this. Now, if you understand how the shaft operates, you understand why it is negated. Okay? Its negative rotation causes the movement of the fluid forward. I mean, when you see the structure of the pump, you understand why it is this way. So keep this formula also in mind. The formulas I'm giving to you, please write them down. Please write them down. Write this formula. Look on the left. Write this formula down, but assume alpha is equal to 1. So write the formula on the left down. Assume alpha is equal to 1. We'll be using it for calculations. And because I can't really write as I want to, so I won't be able to duplicate it here. So write that down. Then we'll continue. So that's the Bernoulli equation, where the pump is present and there is friction in the pump. That is also considered. Now the HF is not only the friction in the pump. We have to understand that the HF is the friction in both the line and the pump. It is a summation. The fluid flows through a certain pipe. In that pipe, yesterday we concluded that there will be a certain friction, HF. So there is HF for the pipe, and when the fluid gets into the pump and the pump pumps it, there is a certain friction that happens in the pump too, also called HFP or HF of the pump. So the summation of these two frictions is the HF we have in the equation. Is that fine? All right, so let's continue. No, we are not coming to this today. Flow meters will be tomorrow. Okay, I think that's the major thing on pumps. Another thing we'll look at is how to calculate the HF for laminar situation and for turbulent situation. We'll look at how to calculate it. So let's just go to our, let's go and pick a question before we go to the slide B. Let's go and pick a question. I think it's something similar. This one, it's so that you'll be okay with how to go about the Bernoulli. And it also involves the pump we just studied. So having the two, I think you'll be good to go. Let me see how I enlarge the question. Okay, it's fine. All right, so let's pick that end. Let's see. So a pump, we are looking at question 5. hope I can draw safely. You are looking at this question 5. So a pump draws a solution with specific gravity 1.84. Now the solution was not given. And looking at the specific gravity, we can assume it's not water. So the specific gravity is 1.84. And we know how to calculate the
Answer.
density. Yep.
Sorry, there's a question. So the question is,
Okay.
in a case where there is no pump, does the total HF become the HF only of the pipe?
Yes. In case there is no pump, yes. Is that fine? Okay, let's continue. Why did that? Oh, man. Don't go again. Okay, so the specific gravity is 1.84 times 1,000 will give us 1840. And you know the units, kilogram per meter cube. And please note, whenever you are given the specific gravity, okay, whenever you are given a question, if it is not water, look for the specific gravity. If they've not given you the specific gravity and they tell you it's water, then you can go ahead. Even if they give you water, look through the question and see whether there is a specific gravity. Because if it's at other temperatures, you may get it. I mentioned that yesterday. You may get a different specific gravity from the 1,000 you know. I mean, from the one you know. All right. So it is pumped from a storage tank through a 3-inch, and it's best to be drawing whatever that you are given. A pump draws a solution from a storage tank. Most of the times, if the question hasn't told you that the storage tank is closed, assume it is opened. Are we fine? If it hasn't told you it is closed, let me see how I can draw this. All right, whenever you have a is for the inlet of the fluid into the pump. The pipe, that is the inlet of the fluid into the pump, is called suction line. This suction, suction, meaning we are sucking water. Just take it like that. We are sucking the water from there, or the fluid from there. The pump is sucking the water from that line. Then the second one is discharge. After it sucks, it discharges it after increasing its mechanical energy. So discharge line. Is that okay? Now, knowing the suction line and the discharge line, I think we can go back to our question and see how to go about it. So we have the efficiency of the pump has been given. The velocity in the suction line is 1 meters per second. And I said this is the suction line. So a point here. Any point in the suction line from these boundaries, from here to here, any point in there is 1 meters per second. Is that fine? Because the fluid moving will move at the same velocity through every part of that suction line. So any point on the suction line has a velocity of 1 meter per second. Ideally, it is not true, but we are assuming it is true, sake of the question. Ideally, because of friction, it may reduce, but we are assuming it is true throughout. Maybe the friction is significant, it's not significant. Now, we are, let me draw the diagram again. So I have a fluid, I pump the fluid, and the velocity, that's my V1. I want to note a point here. Point. I hope you can see the point. Here. Just a random point. V1 is 1 meter per second. All right. So the pump discharges through a 2-inch schedule 40 pipe to an overhead tank. When they say overhead tank, it means the tank is above the first tank from which it was pumped. And the discharge is overhead, above the level of the solution. So the end of the discharge, I think that is noted in the second part. Now look at here, from where I'm reading the question. This part, right? It says, the end of the discharge pipe is 50 meters above the level of the solution in the feed tank. So this is my overhead. I am pumping it overhead into a tank. And the position of this tank, I wish I could draw this. The position of this tank, draw this better. Oh, shit. All right, just let's draw it again so that it will look better. Let me see. It's the same thing I want to represent, but okay. So the position of this tank in which we are sending the fluid or discharging the fluid is 50 meters above the feed solution. Now this is the feed tank, and the solution is in there. So they are saying, follow my short dashes. This distance, which is also referred to as change in Z, is 15 meters. Is that fine? Now, if you have that, they said it's above the level of the solution in the feed tank. Frictional losses in the entire piping system is 30 joules per kilogram. Frictional losses in the entire piping system is 30 joules per. And note this, they said the entire piping system is 30 joules. So it includes the pump and everything, the pipe connected to the pump. That is the system. Are we fine? That is the system. So it includes the friction in the pipeline, the friction in the pump, and it is giving us 30 joules per kilogram. So our work has been made easier. There are situations where HF won't be given to you, and you have to apply formulas in finding HF. Depending on what flow, if it is laminar, it means you have to read from, you have to use the formula we'll be looking at later. If it is turbulent, we'll have to also look at a formula later. We'll discuss that, and we'll read from the Moody chart. So take note of that. But in this case, it has been given to us, so we wouldn't have to suffer to calculate that. So what pressure must be developed? When they say what pressure must be developed, I mentioned from the start that a pump is supposed to increase the mechanical energy of the fluid, and the mechanical energy can manifest in different forms. It can either increase the velocity, it can either increase the height, it can either increase the pressure. When they say pressure develop, it means at this point to this point, the pump did a certain increments in pressure. There is a P1, there is a P2. P1 was lower. When the pump pushed the fluid, it increased in pressure, which is represented as P2. So when they say pressure developed, it means the difference between this P2 and P1. So how much increase in pressure occurred? That's what it means, which is also referred to as change in P. I trust that is fine. All right, let's continue. Hey, I hope my slides are not finished. Hey, be careful. Okay, let's continue. I think, so what is the pressure developed? That's the question they gave us. So at this point, at P1 and P2, we want to first find P1, then we'll find P2, then we'll see the pressure that was developed in this situation. Is that fine? I wish I could write, but I can't write, so let me make this screen bigger. Then we'll look at it from here. All right, so this is the diagram I was talking about. This is their pump. That's the pump. And the difference between the feed fluid level and the discharge fluid level is the 50 meters. And I mentioned that that was the same as change in Z. We found our density to be 1840 by converting the specific gravity to density, multiplying it by 1,000 to get that. Kilogram per meter cube. And certain diameters were given in the question. Let's look at that. We were given the diameter of the 2-inch pipe. Please don't assume the 2-inch pipe is for the first one, because in the question it came first. Don't assume this is the first one. Go and read the question well and see where the 2-inch pipe is supposed to be located. It applies to every question you're solving. Read the information well and know what you are doing. The pump discharges through a 2-inch schedule pipe discharge line. Remember, I told you that the second line is the discharge line. This very one is the discharge line. And let's look at the suction line. A pump draws a solution, that's the beginning of the question, with specific gravity that from a storage tank through a 3-inch pipe. So meaning the suction line is the 3-inch schedule pipe. So knowing that, having the diameters, you can calculate area. I think that's one of the simplest parts of the problem. You can calculate the area. So area of the suction, pi d squared, suction over 4. Area of the discharge, pi d squared over 4. Now diameters has been given. Pi is a value. 4 is also a value. So you compute that and you'll be having your areas. My word. Okay, so I think they didn't calculate the area. I mean, they calculated it, but it's down there. Let me just give you the solutions I had while calculating. So my area at the section, I'm coming. So my area at the suction side was 4.4. You can do that on your calculator. Get the answer, write it down. Sorry, 4.7. This is 7. 4.7, 6, 8, 6.
Sorry, Bansa.
Yeah.
I think there was a question. I didn't see it.
Okay, what was the question?
So the question is change in Z always Z2 minus Z1?
Change in Z is not always Z2 minus Z1, depending. Now, I'm coming. There are certain situations where your fluid okay, your fluid is pumped probably to an underground tank. In such a situation, is here, or my reference point is here. Okay, in that situation, my change in Z at the end of the day, the difference must be positive. Do you get me? You can't have a negative height. When you have a negative, that's fine. So just draw out the diagram. When you draw it out, you will know how to go about it. Okay, where was I? Okay, I found the area of the suction, the area of the discharge. That is also 2.1648 times 10 power minus 3. Now, if you have these areas, it means if you have an idea of the velocity, you can find volumetric flow rate. And since density has been given, you can find mass flow rate. So if you know only velocity, you are good to go to find volumetric flow rate, to find mass flow rate, because we have density. Is that fine? So you can just go around that and see the things that you will need. Before that, you have to check our main question. When this thing move. Okay, so a blank page. Now, if you know how to apply the Bernoulli, remember we are trying to look for P1 and P2 so that we'll find a difference, and that will give us the pressure developed. And the equation in which there is pressure is Bernoulli, considering a flow from one point to the other, right? This is a flow from one point to the other. So you can use the Bernoulli equation. You can also use the mass balance, but that is when you need an information from there. So using the Bernoulli equation, I won't write the equation again. I'll just note it. It's here, A, using the Bernoulli equation. You can write it down so that while I move, you follow. Using the Bernoulli equation. Now I want to draw out the diagram again for some 1 or 2 reasons. I want to draw out the diagram again. Let me see how good I can draw this thing. I hope next week we are able to do it in person. Okay. Oh shit. Yeah, good morning. I'm doing my best. So let's say this is the pump. It pumps my fluid. Now I'm just doing this because of certain things I want to represent into my tank. And I mentioned that the distance between this and that, which is change in Z. Hey, is you. Is equal to 15, right? Okay, 50 meters. Now that I have my diagram, I think I can continue what I want to do. Now I can continue what I want to do. Which color blend will be good? Let me use red and see. All right, so this is my diagram. Oh shit. I'm coming. Please, while we are moving through, I don't know if it will be best to be reading the question. What I want to do, I'm fine with God. What's here, come bro?
It
Oh,
is well.
as well, eh? All right, so, okay, this is what I wanted to do. All right, this is our water level, our liquid level. All right, that's fine. Now let's go back. It's a whole question. That's why I'm wasting this time to do these. Else I wouldn't have actually minded. Now let's look at something. Bernoulli is such that you can take any 2 points of the flow of the fluid and just write your Bernoulli equation around it. So far as you have the parameters to be able to solve your Bernoulli, then at the end of the day, you will get an answer. You get me? So what I'm just trying to say is I can pick Bernoulli here and here if I want. So far as I have parameters for that, I can also pick it here and here. I can pick it in this tank and in that tank. In the same way, I can pick it through this point and anywhere. But at the end of the day, I should know what I want to achieve. So we are going to pick our Bernoulli looking at what I want to achieve. I'm going to pick it here. Why? Because I mentioned that in the tank, certain parameters has already been given. Okay, the question told us to find the pressures here. At this point, let's say 1, and this point, let's say 2. Now knowing 1, 2, that is P1. Shit. Come on. That is P1 and P2. I'm done with the question, the A part. But before I can find P1 and P2, I have to know all the parameters in the Bernoulli equation. Let's come back to the Bernoulli equation. I have to know this pressure. Sorry. I have to know this velocity. And I think the velocity for 1 was given, that it was 1 meter per second. They said the velocity in the suction line is 1 meter per second. So I have that. So it won't be much of a problem. Now, the Z, I'm considering this to be my datu, the base, or let me say the ground. I'm considering here. to be my datu. So I will say there is no elevation. So my Z1, this Z1 is known. It will be 0 because there is no elevation. Same applies to my Z2. Now what will be left is my HF, V2 squared, and P2. For this, because I have this already, the efficiency P, WP is another parameter I'll have to look for. So the unknowns are this guy, as well as the pressures, P1 and P2. I don't know them. HF was given as 30, so I know HF. So how do I find P1, P2? How do I find WP? How do I find V2? There is a way. That way is, if I should do more than one Bernoulli, I may be able to find some of the parameters. Okay, considering the question given to me. So I am going to pick here 0 as 1 point and my discharge end. And I'll tell you the reason why I picked those points. As another, let's say 3. So imagine I didn't draw this. I'm wondering how you understand what I'm trying to say. So this is the third part, the 3. Now I'm picking here 0 because the water in here is stagnant. So it is not moving. So in that case, I can find my V1 to be 0. 2, because I said it is open, it is exposed to the atmosphere. So I can get P1 over here. Sorry, P0, not P1. Remember, P not is not the same as the P1 over here. The pressure of the fluid in the tank, which is exposed to the atmosphere, is not the same as the pressure when it is moving through the pipe. Are you getting me? So P naught will be different, P1 will also be different. Now, if I get my P naught, which is actually equal to 1 atm, is equal to 1 atm. 1 atm. The reason why it's 1 atm is because it's exposed to the atmosphere. Now, at point 3, I can find a certain P3. The discharge is also into a tank exposed to the atmosphere. So my P3 at the spout, okay, exactly the discharge spout, because it's exposed to the atmosphere, it is also 1 atm. Remember, the discharge at 3 is not the same as, the pressure at 3 is not the same as the pressure at 2. Because the pressure at 2, it is moving in a pipe. The pressure at 3, it is being discharged to the atmosphere. So take note of that. So in that case, if I have my P3, and I also have this, and let's note that V3 won't be 0. Into my tank. Are we here? All right. I don't like how the teaching is going so slow, because it is being discharged into the tank, and for that reason, it has a certain velocity V3, which we will have to find. Point O and point 3. Writing Bernoulli at this point as V naught squared over 2 plus, however you label them, it is according to you. equal to then it continues that way. Now they are all seeing. Yeah, they see my screen. All right, so when you continue from where we've gotten to, to, remember that we've already done the Bernoulli for P1.1. Sorry. Let me check my diagram again. Point 0 and point 2. We've done Bernoulli for that. That is what we've represented here. So currently what you are doing is the same point 0 and point 3. So for the point 0 and point 3, I'll use the same analogy here. This same equation. I can't rewrite the equation. So I'll use the same equation to show. All right, so let's use this equation. Following my diagram, I mentioned that at 0, the water is stagnant. So my V1 is 0. Is that fine? Then at P1, at the same point 0, my pressure is 1 atm. So it means I have the value for this. Let me use plus for that. I have the value for it. My Z1, that's the elevation at point 1. They gave me change in Z. So what I will do is to rearrange this such that I will get change in Z. Bring everything to the left-hand side and get change in Z. And that is 15. So it means I know the value for Z1 and Z2 because I've combined the two to get change in Z. HF has been given. Is that fine? P2, which is in our question P3, okay, which is P3, is also discharged to the atmosphere, so 1 atm. So if here was P3, I'll have gotten 1 atm. Is that fine? Now, knowing V1, knowing HF, knowing Z, if we meet in person, we'll go through this question again. Now, knowing Z2 and Z1, by arranging them to get a difference, which is 15, I'll be able to find, I hope you know you can find V2. How to find V2? Let's go there. How to find the velocity 2. You know, velocity at currently is 3. We are labeling it as 3. So velocity at the discharge. The velocity in the pipe over here will be the same velocity here, the same velocity here, the same velocity at the discharge. Because the pump is pumping the fluid with the same velocity or increasing it by the same velocity. So at the end of the day, through this, we'll be having the same velocity throughout. So at point 3, my velocity will be the same as point 2. V2 is equal to V3. That's what I mean. So if you have your V2 to be equal to V3, now you know the diameter of the pipe 2. We found the area. We found A2 in our previous calculation. We found A1. So knowing A2, I can just go ahead and find the velocity. The velocity. Again, note that for mass balance, the amount of fluid that will enter this part will be the same that will come out from here. So I can say the mass flow rate at point 1 is equal to the mass flow rate at point 2. Mass flow rate at point 1, mass flow rate at point 2, they are equal. Density, velocity, area, 1, 1, 1. Density, velocity, area, 2, 2, 2. In this situation, the densities are the same. The areas, we found it. We found these areas. The velocities, okay? The velocities, we know V1, which is 1 meter per second. So we can find our V2. When we find our V2, we can now come and substitute it into this question. Now, our efficiency is 60%. That's 0.6. So I can find the work of the pump. So at the end of the day, the work of my pump will be equal to, yeah. Is there a question? I should. Hello? Okay, let's continue. So at the end of the day, I can find my WP, making it a subject from this equation. If I get my WP, which is the work of the pump, okay, I'll get a certain value. If I get that value, later we'll go into the solution and see how they went about it, and I'll explain that to you. So if I get the work of the pump, the next thing to do is to now go and use the first Bernoulli we did between point 1 and point 2. Our first Bernoulli was between point 1 and point 2. That will help us find P2 minus P1 over rho. If you do it very well. So let's say point 1 and point 2. If I go back to the diagram, you understand what I'm trying to say. If I go back to the diagram, so this is my point 1, this side. Sorry, here. And this is my point 2. Now at point 1, point 2, doing the Bernoulli over there, we have pressure unknown because it's moving through the pipe and we don't know the pressure. We have P2 also unknown because the discharge line, we don't know the pressure over there. So what we will do is to actually group it such that we'll be having P2 minus P1 over rho. This is the same as change in P over rho. Is that fine? We will group the Z2 and the Z12, sending the Z1 to this side. We will send this P2, P1 here. The sign changes to negative. We now have V2 and V1 from the calculation we did. So we can send the V2 also to that side. I mean the V1 to where the V2 is to get V2 squared minus V1 squared all over 2. HF is known. WP, we have calculated it. Efficiency, we know. The only parameters we don't know in this case, let me see whether I can write that formula down so that we pick it from there. So currently what we have is change in P, that's P2 minus P1 over rho, plus change in V squared. Bear with me if I'm using a shortcut, but I believe you understand what I'm trying to say. So change in V squared over 2 plus change in ZG. Is that fine? We are sending everything on the left-hand side to the right-hand side. so that it becomes Z2 minus Z1, P2 minus P1, V2 squared minus V1 squared. The HF will still be positive, but the NP, WP will now be negative when it comes to the left-hand side. And all that will be equal to 0. What we are trying to find is this. Now we have the value for all this. We have the value for change in Z, which is 15. Gravity, we know. HF, which is 30, was given in the question. NP 0.6. WP, we found it. So at the end of the day, I'll be able to get my change in P over rho. I'll be able to get that increase that I'm looking for. Now remember, change in P over rho is not the answer. What they are asking us to find is the pressure developed. That is change in P. So whatever answer I get, I'll multiply it by density to get a pressure developed. It's quite unfortunate. The slate isn't here for us to write, but let's just go it that way. Now, after you get the pressure developed, there is a second question. The second question says, what is the power of the pump? And remember, we found WP, which is the work of the pump. Note that work is Joule. In this case, for the Bernoulli equation, work is Joule per kilogram. For the Bernoulli equation, that's the unit. Where am I? Okay, so my work has a unit of Joule per kilogram. So if this is my work, then I can find my power. Now, what are you doing here? Let me just use this. Kilogram per second. So my power will be mass flow rate times the work. These two cancels each other, and I get Joule per second, which is the same as watt. So that's just CPC. So if you have that, then I think we will be done solving that. That's the end of this very question. Of question, then I'm sure you're okay. Difficult. And that's why you're not moving fast. Okay, so let's continue. I want us to pick another question. Yesterday, I mentioned that you guys should reach me, but it seems only a lady reached me. And I gave her some questions to solve. And yes, I won't resend that question to anyone. She alone will solve it. Because you decided to refuse to reach me. But they are just practical examples in the tutorial questions, just to help.
Bansa.
Yes. Hello?
Okay. So the question is that you kind of go through the solution. So I can just quickly brush over the
All right,
solution.
so going through the solution. So let me start that. A pump draws a solution with a specific gravity of 1.84 from a storage tank. So you change this to density. That will give you 1840 kilogram per second. And through a kilogram per meter cube, through a 3-inch schedule 40 steel pipe, the efficiency of the pump, that's NP, is 60%, the velocity in the suction line, and I told you that the suction line is before the pump. The suction line is before the pump. So the velocity in the suction line, so any point along the suction line, is 1 meters per second. The pump discharges through a 2-inch schedule 40 pipe to an overhead tank. So a tank that is above the inlet tank from which the water is being drawn. The fluid is being drawn, sorry. So it is above, and they give by how much? They said the end of the discharge pipe is 15 meters above the level of the solution. So if I have my solution here, the discharge line is here. Now the difference between these two, change in Z, is 15. Above the level of the solution in the feed tank. Frictional losses in the entire system, including the pump and the lines, is 30 joules. What pressure must be developed? That is the question. What pressure must be developed? And I mentioned that when we say pressure developed, it comes from the definition of what a pump does. A pump is supposed to increase the mechanical energy of a fluid. So if it should manifest as pressure, then it means my pressure at this point, the suction point, and the pressure at the discharge point will be different. Here and here will be different. So we want to find the difference. That is what we call developed. And I named it as P1, P2. That is what we call developed. We want to find the difference in the two. And the second question is, what is the power of the pump? To find the power, we have to find the work. That's one thing you have to know. Using the formula, power is equal to mass flow rate times the work of the pump. So let's go to the solution. In the solution, we have 0.3 and 0.4 as the suction and the discharge. 0.3 to 0.3 to the tank. Any point along that line, any point along this suction line has a velocity of 1 meter per second. Any point along this discharge line has a velocity, including where the 2 is, has a velocity of unknown, V2. We will have to calculate it. Now, noting that very well, the diameters of the suction point for this side was given, and the diameter for that side too was given, meaning I can calculate the area. Now, when I get the area, I know mass balance is the fluid that should, the mass of the fluid that should enter the pump should be the same as that comes out. Do you get it? Should be the same as that comes out. So mass at 0.3 is equal to the mass at 0.4. And we know mass can be expressed as density times velocity times area at 0.3. Density times velocity times area at 0.4. In that case, I can find the velocity at 0.4. Remember, we don't know the velocity at 0.2. Let me write it well. We don't know the velocity at 0.2. But when we find the velocity at 0.4 here, when we find the velocity there, we know that along this line, at every point, it should have the same velocity. So the velocity at 0.2 will be equal to the velocity at 0.4. Now, coming back to our formula, the Bernoulli equation. This is it. All right, so the Bernoulli equation, they picked P1. They picked 1. That is the point in the tank. I told you Bernoulli equation is for flow between 2 points. So at point 1 and at point 2. And they picked it because they had enough parameters to calculate it. And I was explaining. For instance, they said at point 1, the pressure at 1 is equal to the pressure at 2, which is equal to 1 atm. Why? Because the pressure at 1, the tank is exposed to the atmosphere. The pressure at 2, the water is being discharged to the atmosphere. So it's 1 atm at the end of the day. Now the velocity at point 1 in this tank is 0 because the fluid is stagnant in the tank. In the pipe, it is moving. That's at 1 meter per second. But in the tank, it is stagnant. That is why we have this V1, 0. Now, knowing this, P1 equal to P2, it means P1 will cancel out P2 if you should arrange them because they are the same. If you should send it to the left-hand side, right? P1 to the left-hand side, they will cancel out. V1 is 0, so this guy is gone. Is that fine? Now, we have Z2. We'll bring this here to get Z2 minus Z1. And that's what we have over here. The NPWP, I think they rather did the other way around. They brought the Z1 to this side. But however you do it, at the end of the day, when you do, that is mathematics. When you do it well, you should get the same answer. So V2 squared over 2 plus HF, the terms on this side. This is what is left, as well as this. These are the things left. HF is a value known. V2, we don't know. But as I mentioned earlier, we can use the mass balance. Sorry, it's here. We can use the mass balance to find V2. So if V2 is known, then what will be left? Z1 and Z2, the difference is change in Z. So change in Z, we said is 15. It should be actually Z2 minus Z1. When you do it, you get a negative answer. They will negate it over here. That's what I'm trying to say. Here, they will negate it in their solution. But at the end of the day, if you should do it very well, you will get NP has also been given. So this is out. What we are left is WP, which is the work of the pump, what we need. All this they have over here is the calculation for the velocity at 4, at 0.4. And I explained that here, up here. Now, after finding the velocity at 0.4, I can say the velocity at 4 is equal to the velocity at 2, knowing that through the pipe, the same velocity will flow. If you remember this. Now, the fluid will flow at the same velocity. Now, knowing this, V4 will now be equal to V2. That's 2 meters per second. So I can substitute the value of V2 in there. And after substituting, I have my efficiency, I have my V2, I have Z2 minus Z1. Now they've corrected it. I mean, they've arranged it well to get the 15. I know G 9.81, HF is 30. So I can find my WP now. So there's a value. Now I go and do another Bernoulli. This Bernoulli is now to find change in P. Remember, before you can find change in P, this WP must be known. And the only way to know it is by using the first Bernoulli we used. You get it? So in that case, to find change in P, which is the pressure developed between these two, change in P, pressure developed, right? Between 0.3 and 0.4. That's why we are picking the Bernoulli. Remember, 0.3 is in the suction line. 0.4 is also in the suction line. We have velocity for 3, that's 1 meter per second. Velocity for 4, we just calculated it. We have pressure for, do we have pressure for any? No, we don't have pressure for any. But we can write that pressure as change in P. Is that fine? Now, the work of the pump, we found it. Efficiency too, we found it. So let's go back to our formula so that we can go through that. So let me see. So we will rearrange this. This comes here. This comes here. This goes that way. Now what I'm looking for is P4 minus P3. That is called change in P. This is it. Making that a subject, I'll get this. Now HF. Okay. They claim HF is small. The truth is you can introduce HF and calculate, but at the end of the day, you get small. HF is small because you are picking only this point and this point. So this point and this point. So we are neglecting the pressure along this line. So we can't call it 30 again. Remember I said we are neglecting the friction along this line. So we can't call it 30 again. Remember we said the friction HF total is equal to the friction in the lines plus the friction of the pump is negligible. It's very small. That is why our HF goes to 0 because of the points we picked. Remember, F was neglected. Now, if you should continue your calculation, I won't say the answer we'll get will be very accurate because at the end of the day, our P4 minus P3, which is change in P, which is what we are looking for, is 60%. This has been found. So just substitute. You get this value. P4 minus P3 over rho. And for that reason, it's to be change in P over rho. So whatever answer I get, I have to go back there and multiply it by the rho. That's why the 1840 is here, is the density. Mass balance tells at the suction line to solve or the velocity here to solve, we will get the same answer because the areas are different and the areas will compensate to make them the same. So at the end of the day, you get this answer or an answer close to this. No matter what formula you should use, just note the mass flow rate. WP has been calculated already. Substitute, you get your answer. There is also another way to solve the mass flow rate. Is that fine? Wow. We've really used much time in solving this. Okay, so I think I'm done with this. Let us go straight to the slides again, or her notes again, and let's look at something. Again, today, what I wanted to achieve, we couldn't achieve it. All right, so I want us to, any question? I want us to stay on friction a little because the next question we'll be solving, maybe not today, will be on friction. We have up to 11 o'clock to close this class. We are hoping to be able to solve a question. So there are two kinds of friction, skin friction, form friction. Skin friction occurs usually in laminar situations, laminar flow. Form friction occurs usually in turbulent flow. And one thing you have to note is they all have different formulas for their representation. Yesterday we looked at this, that is for laminar. There is also this formula, the Hagen-Poiseuille's equation. I think that equation is for laminar flow only. So note that the equation is giving us this. This is not in the bracket, but I'm putting in the bracket. It's a very important equation. So it is for laminar situations only. If you use it for turbulence, you'll be wrong. So it's either this. There are different ways of finding HF Remember the question we just solved, they gave us the HF, but there are questions, situations where HF won't be given. So in that case, you have to calculate for it. So you have to know whether the flow is turbulent or laminar. And flow in pipes, after calculating the Reynolds number, you can know whether it is turbulent or laminar. Is that fine? If it is laminar, you use this equation we have over here. Note this relation. FD equal to 4F. There is one is called Darcy's friction factor. The other is called Fanning friction factor. Fanning friction factor. Now there is another formula for HF. This is for both laminar and turbulent situations. So whenever you have a turbulent situation, you use this formula. Okay? You use that formula. This. Now note very well that in this formula, there is a certain term called FD. That is the Darcy friction factor. Now, the Darcy friction factor has two parameters that you have to always calculate in order to be able to find the Darcy's friction factor. That is Reynolds number and relative roughness. Reynolds number, you know how to calculate by now. Relative roughness, before I go back to Reynolds number and relative roughness, there is another way to also calculate the friction factor for. This was by an experiment. Another way to also calculate the friction factor for laminar flow. Remember the first one, we looked at this equation, this very equation, right? Now, there is also another way, which will give you a rough estimate. That is this, 64 over Reynolds number. And it is correct when you use it. Just calculate your Reynolds number. Then 64 over Reynolds number should give you the answer. Is that fine? FD. This is for the Fanning friction factor. The other is HF, sorry. Please know the difference. This is for FD. So back to the FD. The FD, if it is not laminar, you will have to calculate Reynolds number and the relative roughness. But if it is laminar, just use this formula over here. The formula down here, 64 over Reynolds number. Calculate your Reynolds number, it is laminar flow. When you use this, you still get the answer. But you have to go and read from the graph. That will be a long process. Now, let's remember that when you calculate HF, it is in the unit joule per kilogram. You can be asked to write it in the form of hertz, meter. Okay? Hertz, that is in meter. Just divide by gravity. Just divide your HF by gravity. And you get it in hertz, meter. So let's continue. The relative roughness can be calculated knowing the absolute roughness. The next time we meet, we'll take a question. But before that, I'll give you those questions so that you go and try your hands on, even before we meet, so that it will be faster. Okay? Now, in the pipe, the inner surface of the pipe, the roughness may not be the same. It may vary. I'm just drawing something for you to understand how it may look like. So if you don't pick relative roughness, that is the diameter, which is this distance, with respect to the thickness of that roughness, you may get it wrong, or you may not get a very good answer. So usually absolute roughness has been given in a table. Please always, although you may chew the absolute roughness, always try and check the table before you solve. Don't become too familiar. Sometimes they use stainless steel pipe, sometimes commercial steel pipe. they change them. So make sure you check and see what changes has been made so that you will know which absolute roughness to use. When you get the right absolute roughness, remember the unit is in millimeters. So when you are giving your diameter, sometimes it will be in millimeters. Don't change it yet. Although later you will change it, but don't change it yet to any unit. Leave it in the millimeter. Calculate the relative roughness, which is the absolute roughness over the diameter in millimeter. Then whatever value you get will become what you need to read your Darcy's friction factor after calculating your Reynolds number. This is very important because this will be what we'll be reading from the Moody chart. All right, so I think knowing this, you should be fine with the kind of questions that will come. And it will just be like the same kind of pump question we solved. Maybe it won't be Bernoulli intense as I did. In case there should be a calculation for the Fanny friction factor, I mean the Darcy's friction factor, and that will help you find the HF. And that will help you put that equation in your Bernoulli equation. Now we want to look at how to go about reading the Moody chart. I know some of us know how to read it, but I'll take my time so that we go through together. Now, this whole Moody chart concept is to find what we call the FD, Darcy's friction factor. It is to find this. Now, note very well that to find FD, you have to know Reynolds number and relative roughness. I've taught you how to find the relative roughness. Reynolds number, you know how to calculate it. After getting those parameters, you can now come to this chart and read your FD. Now, the question is, what we use FD for? Remember the formulas we saw earlier. This, for instance, I hope you can see that. Yes. So this formula, there is FD. To find my HF, there is FD. So I have to find the FD. The length of the pipe most of the times will be given. Sometimes the length of the pipe, later we'll go through this again. The next time we meet, we'll go through this again for you to understand, but just to get the concept. The length of the pipe may be the total length. In your calculation, there is a pipe length, there is a pump. So at the suction line, there is a certain length. At the discharge line, there is a certain length. In the pump, remember the fluid covered a certain distance in the pump. That is usually represented in length equivalent, LE. So that length equivalent will have to be changed. It's usually given as, sometimes they'll tell you 200 diameters. When you see something like 200 diameters, it just means multiply the 200 by the diameter of that pipe. When you multiply it by it, you get your length in meters. Function length as well as the discharge length. And that will give you the total length. In this equation, back to this, okay? In this d v squared over 2. In this equation, note that whatever length they ask you to calculate is the total. Go there now. You must use the total length for now. Later, I'll go to how to go about the velocity head approach. So use F. Remember, I said HF is the friction across both the lines and any fittings or valves or whatever that may be in the line. When you use the total length, it means you said earlier is to get FD. When I find FD, I come and find my HF. Knowing my total length, knowing my velocity, is that fine? And what is here? Is it 4? It's FD. All right. So knowing my FD, then I can calculate my HF. Now, if there is any further question, I can go ahead and do it. Maybe place this in the Bernoulli equation. We know our Bernoulli equation has HF. I can place it in there and solve whatever I have to solve. Is that okay? So I'll end it here for now. And we will see if we can finish up with 1 or 2 questions in this. Kindly, again, kindly reach me. Kindly reach me. I will place you in a group. I will put the tutorial question there. In case you already have it, then there is no problem. But I would like you to still reach me because I will be sending other materials in there for you to use. So kindly reach me. Let me place you in that group. And I would like you guys to let me go back to yesterday. The questions I gave out to those who were able to reach me. I'll give it out again. Go and study them. And please, when I say go and study them, that doesn't mean that is what is coming. To just clear your doubt. And please, I don't know what is coming. In fact, I don't know how the questions will be set. I don't know. So it's just for you to calculate more on what we did earlier. So you realize that the questions are what we've done. Do you get me? So it is just to help you. I don't know what is coming. Now let's look at the questions. Question 5. Write them down. Question 5 in the tutorial questions. Question 20. Today we did question 5. Look at it again. Question 20 in the tutorial questions. Also look at question 15. You can play around these ones. Question 11, question 34, and question 37. Just write them down, solve them out. And later when we meet, we may go through them. In case we don't, I think the tutorial has its solutions. So I'll send the solutions and you just check it out. Okay? But I hope we do. I hope we do. So it's already 11. Otieku.
Yes, please.
Otieku, are you there?
Yeah.
Yeah, I think my time is up. Otherwise, we'll
Okay,
use
so
6 hours.
let me stop the recording and I want to say something. Let me stop the recording.
Okay, sure.